Hi there, I'm Cole, and this is my Math Sci 104 extra credit assignment video. So those three videos shown right before this are all taken from my camera roll when UCLA got super flooded during those crazy rainstorms in this last winter. And one of the most pressing questions from this is, how does that water become drinkable? Because as we see, the water is sitting there puddling at UCLA, collecting all of the nasty contaminants on the ground. You don't want to drink that water straight from the puddle. To make that water drinkable, environmental engineers often use treatment systems such as the one ASCE's environmental design is using here. For this assignment, I'll be discussing and doing a live demonstration of the properties of one of the most powerful materials in water treatment, which is granulated activated carbon, or GAC. All right, let's get started on our demonstration on how GAC is used in water treatment. So right here we have our GAC. You can see it right there in the container. But before we get into the demonstration, I'm going to talk more about GAC's properties and the material science behind it. Like the name suggests, GAC is an organic compound. Now, these organics can range from coal, wood, and there's many other options too. But basically, these organics are activated using heat treatment. This heat treatment creates the porous structure that we see in the picture. Now, this porous structure is extremely powerful and useful in water treatment. Through a process called adsorption, many contaminants are more attracted and more likely to get stuck in the GAC than they are to stay in the water. This pretty much means that we can remove contaminants from water by running it through GAC. Let's move on to the demonstration. So here I am constructing the system that the water will be run through. I'm using a micron sheet pretty much just to hold that GAC I'm putting it now. The water can flow through both the GAC and the micron sheet. For the sake of this demonstration, I'll be showing that GAC can help to remove oils such as sesame oil from water. So here is our influent, that's what we call the contaminated water, and I'm running the influent through this system. As you can see, I'm trying to maximize the interaction of the influent with the surface area of the GAC. I want it to touch every bit of that GAC. Again, I don't want to pour it all through the same spot and get it clogged. So here you can see that nice flow. You see the water is flowing through that GAC and through that micron sheet into the bottom. Now, I will mention the micron sheet is also helping to filter out some of the oil, but the GAC is really doing the heavy lifting here. So this is our influent right there. Look at that. That has a lot of oil in it. Also notice that the oil rises to the top of the water. Bam, we have our effluent right here. Look how clean that looks. The GAC did its job so well. And here's a little side-by-side comparison. Look at the difference. The GAC did a great job. Now, one downside to GAC is that eventually the pores will clog and it needs to be either cleaned or replaced. So this is a not really industry method, but a method that the environmental design team does. We pretty much rinse out a GAC with water until it is clear. You can see that water is not clear, it is very black. But in industry, it's very common to just reapply heat treatment to the GAC and pretty much activate those pores again and get rid of all the contaminants within them. Overall, the material science of GAC is a total game changer for water treatment. Again, that porous structure allows the GAC to absorb contaminants from water, pretty much letting us have clean water that is not going to poison us over time, which is obviously so important for so many water treatment plants and facilities. My only source for this video is the EPA, and it is listed right here. Thank you so much for listening and learning more about the applications GAC has for water treatment and how its material science contributes to this.